can be proved is smaller than the variance of a priori. Now, it means that if I look at the variance of a priori, that variance has a certain behavior. And the variance is describing the spread, so the uncertainty on the estimate of the parameter. So it comes out that if I use the data, my variance is smaller than without using the data. So my variance of a posteriori is always smaller or equal than the variance of the a priori. Statement number one. Statement number two. Comment number one. Okay. So comment number one is what is written. So comment number one is important. Okay. So that means that using the data and the a priori gives an uncertainty that is smaller than the uncertainty that I have without making the measurement. Okay, so which means if you estimate my position and you are sitting at home, you have the variance, which is the a priori. If you estimate where I am and you are here, you got the variance that is smaller. Okay, because you are making measurement. So making measurement is reducing the variance. Good. Okay, good result. Intuitive, but you know, it's numerical. But we have another one. So, I mean, looking at this one as another property. The other property, let me say 1 prime, is that sigma 0 square is also smaller or equal than sigma w. And sigma w is the variance of theta at maximum latitude. So, since sigma 0 is equal to the variance of theta given x, the variance of theta given x is smaller than the variance of the maximum latitude, which means using the a priori reduces the variance, which means using the a priori is making the estimate better. Okay? That's why I say 1 prime. Okay? Now, let's move forward. What's happening here? Comment number 2. Comment number 2 is saying that the estimate is Gaussian. So, now this property is general. So let's see, you know, what that one is describing. It's saying that if I have an a priori that is Gaussian, and if I have a conditional probability density function that is Gaussian, then you know, combining the two, I get the Gaussian. Okay? So that means that if my a priori on theta naught, okay, that is a p theta, and p theta is Gaussian. Okay, so theta a priori was considered to be Gaussian with a certain dispersion. Now, after, you know, if I look at the condition of PDF, the condition of PDF is Gaussian. The a posteriori, okay, is Gaussian as well. So this is the p theta given x is Gaussian. So that comes because when I calculate the p theta given x, I have a p s given theta that is Gaussian times p theta that is Gaussian. When I multiply two Gaussians, the result is Gaussian. So if this one is the a posteriori, and if I ask you, you know, where is the maximum? Well, if this one is Gaussian, remember, this one is Gaussian, then you know the maximum coincide with the mean. Because the mean and the maximum coincide. So we can say that in this special setting, if the a posteriori probability density function is Gaussian, then theta at maximum a posteriori coincide with theta MMC. So map and MMC coincide in case of Gaussians. So that means that I don't need to get crazy to see. I mean, if I need to calculate the estimate according to the map criteria or the MMC criteria. Okay, that's another property. So that one is Gaussian. So that is exactly what is written there. So the a posteriori probability density is Gaussian in theta, where the mean is Gx, and the dispersion is sigma t. Now the mean, okay, so that one is the mean, Gx. But since the mean coincides with the map, coincides with the MMC, this is the MMC estimate. So Gx is the MMC estimate. So that's a Gx. So by looking analytically, what is Gx? Gx is what is indicated there on the top. So Gx, okay, is the maximum and the MMC estimate. Here. Now let's look at. Okay, so otherwise we can look at here. That's the result of the comment. So the estimate theta map is the mean plus a scaling factor multiplied by x minus the mean. So look at now, that means that if sigma theta now is very big, okay, assuming that sigma theta is so big that it is going to infinity, okay, so that means that my a priori formation, is getting bigger, bigger, bigger. Sigma is getting bigger, bigger, bigger. If this one is getting bigger and bigger, what's happened is that this distribution, it means that the theta can be everywhere. So if a sigma theta is going to infinite, the a priori becomes non-informative because it doesn't tell anything about the parameter theta. Okay, so if a sigma theta, okay, so if sigma theta is going to infinite, okay, then we can say that a priori, it doesn't tell anything about what is the value of the parameter. Then we say that the a priori is non-informative. Sometimes another way to say is diffuse. Okay, so it's non-informative. It's not constraining. Where is the professor in the world? Okay, I know. It doesn't tell anything. Okay. No, it tells that he's alive, actually. Okay, but it doesn't say anything. Okay, so when I say the broader is a sigma theta, the less informative it becomes. Now, what's happening if sigma theta, is going to infinite? Now, if sigma theta is going to infinite, I have theta plus. Now, if sigma theta is going to infinite, this sigma w counts as nothing. Okay, then this one disappears. So I have theta minus x, so plus x minus theta. Okay, so it comes out in this case that theta map that we know that coincide with theta and MMC is equal to theta naught plus x minus theta naught, which means that is x, which is theta maximum likelihood. Okay, so if the a priori is non-informative, I collapse my estimate, reduces to the maximum likelihood estimate. Okay. Now, on the other hand, if sigma theta now becomes much smaller than sigma w. In other words, means that, you know, sigma theta, in this case, okay, is narrow than the dispersion of the noise. So what's happening in this case? So it means that this plus that, you know, is dominated by sigma w. So, you know, I have a theta naught plus, I mean, this number, okay, is a small number divided by a big number, okay? So small number divided by a big number makes this term approximately 0, or at least negligible with respect to the other. So I have a theta naught plus small number, okay? So, and in the limit, this becomes a 0. So if, you know, if I make virtually sigma theta close to 0, so approaching 0, then it comes out that the theta map coincide with the theta MMSE, coincide with theta naught. It does say, it says the following: if the noise, okay, the condition which dominates is this. So if I am in a big mess, so if I make a measurement, you know, my measurement is very noisy, okay? So it's better to take the measurement, throw away, and keep the a priori. That's what it's saying. You know, in other words, imagine that, I mean, when you make the measurement, you want to estimate my position. Huh? You know that my distribution is Gaussian around this position now. You know, and then let's assume that, you know, taking the measurement, you open the door, you try to estimate, it's a mess. Okay? The estimate is very, very severely dispersed. So it's very, very highly noised. Now, if you need to establish what is the estimated position, you know, the safest is to say that the a priori dominates. So it's a trade-off. So you have, you know, the balance between. So it's like, you know, it's a pulling two forces, okay? So you have the estimate theta hat, okay? And, you know, it's pulling on one way and another, okay? And it's pulling the a priori on one side, and it's pulling on the other side the data. Data means maximum macro distance. Now, if, you know, if the a priori is loose, it's not strong, okay? So this kind of spring, you know, is not pulling too much, and it goes on the other side, and I get the maximum macro distance data. If on the other side, you know, my data is not strong, it's very noisy, the a priori dominates, and, you know, the estimate pulls on the other side, which means on the a priori side. So, and, you know, the estimated value is halfway. Now, we get one important property, which you mostly always, I would say, 99% of the time you forget when you are on the exercise on the practical case. The estimate is equal to the mean plus blah blah the error. Okay? So, you know, if the mean is 0, if theta naught is 0, okay, so the estimate is 0 plus blah blah x. Okay? So that means that, you know, my estimate is pulled, is pushed, okay, to be close to theta naught, which is 0. So, you know, 0 is really a position where you don't take any position, you don't take any, you don't unbalance from one direction or the other, okay? And so, sometimes, when you don't know what to say about the a priori, you say that the mean is 0. Now, when you estimate, you got the estimated that, you know, since this one is 0, is a multiplication factor multiplied by x. Now, this multiplicative factor is different from the maximum likelihood. It's taking apparently the maximum likelihood and bias the maximum likelihood. is biased, because if you look at that, you know, this multiplicative factor is multiplied by x, and this multiplicative factor is reducing the value of x, because the maximum likelihood estimate is x. For this reason, sometimes you get the impression that the MMSE estimate is estimating a value that is lower than the value that should be. This is due to the fact that the MMSE or the map is a balance between a priori, that in this case, you know, in the case is theta, but if theta not is 0, then it's 0. So it's a balance between 0 and the maximum likelihood estimate. So then, you know, it's halfway. So expect that. Don't be surprised in case your estimate, you know, is pulled to 0. Is, you know, is attracted by the 0. Is more or less attracted according to sigma w. Okay? Because, you know, it's attracted according to the sigma w. So if it is very, very noisy, okay, like in this case, okay, then, you know, it's attracted by 0. Asymptotically, it says, if I don't know what to say, I say 0. If I don't know what is my estimate, I estimate 0. Because 0 is neutral, you know. It's like taking no decision. It's like no estimating. No. Ah, here it is where they are. Okay, we said, let me check if we said all.
So in the case, for example, that we have the noise that is too big with respect to the variance of theta, so we can say that the fact that, for example, in the frequency estimation, we saw that when we have a signal to noise ratio which is very low, the estimate of the frequency, what we can say, the best we can say is that is only between minus pi and pi.
Yeah.
So we can make such a sort of a comparison with this example.
In fact, if we have a very low signal to noise ratio in frequency estimation, if sigma w is so big, you know, my frequency is, I mean, my estimate is between minus pi and pi. And so, since it can be everywhere in that region, then I say that's uniform between minus pi and pi. And since it's uniform between minus pi and pi, then, you know, my error is related to a uniform distribution of estimate between minus pi and pi. And that's the case. So in that case, you know, let me see if I find it. Give me the book. It's easier. That's, you know, this is the plot that we are discussing, okay? That we saw together during the exercise. We saw it. Then, you know, I mean, if this plot is showing the mean square error versus SNR, and you know, we saw that this plot is characterized by a saturation region due to the granularity of the Fourier transform. Then in this region goes as much as the Kramer-Rao bound. But when the signal to noise ratio is very, very slow, very, very low, then, you know, it departs from the Kramer-Rao bound. Now, in principle, if we are not constraining the estimate to be between minus pi and pi, which is an a priori information, so if we are not constraining, this plot should go this way, which means departing, you know, larger, much larger than the Kramer-Rao bound. But because of we are constraining our estimate to be between minus pi and pi, so, you know, this plot is, rather than growing up, is limited to this interval, because my error cannot be larger than minus pi and pi. Now, this level is due to the a priori knowledge about the fact that the estimate is limited between minus pi and pi in terms of error. That's an a priori information. So I'm using the a priori information about the interval where I'm limited to. You push me, you put me another case on the maximum on the Bayesian estimate. Assume that I tell you that the parameter R is a power. So the parameter theta is a power, and the power is larger or equal to 0, so it cannot be negative. Okay, assuming that I'm measuring the power of a signal, and I know that the power of the signal cannot be less than 0. Okay, so I have a signal. It's not that because I'm giving the power to the signal, so the signal is giving the power to me. Now and I want to estimate the power. Okay, so when I estimate the power, I'm saying that the power is larger than 0. Now, so let's make the problem general. Assuming that I estimate the parameter, and I know that the parameter is larger than 0. Assume now that I calculate the probability density function of x given theta, which is the Laplace function. Okay? Now assume that this Laplace function, this is 0, is behaving this way. Okay. Now, so the maximum Laplace is this. Right? Because the maximum Laplace says, take the maximum of the Laplace function. Stop. Right? Now, but I mean, since theta should be larger than 0, then I'm not taking that. I'm taking this. Okay? So I'm neglecting all these values. What am I doing? What is the process that I'm doing now?
You are using a priori information to...
I'm using a priori information. So I'm using the a priori information which is set 0. And then, since I know nothing what's happened with the value larger than 0, so my a priori information, okay, is uniform after 0. But I'm cutting everything before 0. And this way, I'm using the a priori information. So I'm cutting out the values lower than 0 means that I'm making a maximum likelihood. I'm making the is it called? I'm making the Bayesian estimation. Okay, that's what implicitly is happening. Another example, which is similar. Another example. Estimate theta. But we know that theta is limited between A and B. So estimate theta limited between A and B from X. Now what you do, okay, you take the Px given theta, okay, which means you are making the maximum Laplace method. So your Px given theta is, sketched this way. And I'm limiting the value to be, between A and B. So if I limit my search between A and B, because I mean I know that the data is limited between A and B, that means that I'm taking all the values and multiply by a function, and this function is 0 everywhere, and is limited between A and B, and is 0 after B. I'm using the a priori. Because when I say estimate theta between A and B, means that I encode, I represent this information as a uniform probability a priori, uniform a priori probability between A and B, that is multiplying the conditional PDF such that the search is only carried out in this interval. It doesn't matter that the maximum lateral is bigger here. This value is not compatible with my search interval. So when I tell you search the estimate limited between this and that interval, I'm telling you an a priori information. And you are making a Bayesian estimation. Okay. Now, up to now is all good news. Now, let's start. Okay, these are the variants, the discussion of the variants we already did. Oh, I have a multiple observation. But you know, let me go here. Let me go to the bad news. So up to now, you know, it's easy. Okay, so we said, okay, so theta is Gaussian, tau is Gaussian, that's fine. Now, let's look at the case where I have a non-Gaussian a priori and Gaussian noise. So let's consider the model where, I mean, when I have a measurement x, so in x, I have a x is equal to theta plus w. And you know, x is a random variable, which is a sum of theta as a random variable plus w, which is another random variable. Now let's assume that one of the two is non-Gaussian. And now you know this is the trouble. Because what's happened is the following. Now, if one of the two is not Gaussian, then I need to compute the MMSC estimate. I need to compute the estimator, the specific estimator. Now let's start with the MMSC. Let's assume that, you know, only one of the two, which I choose in this case, W. Oh, so let's assume that W is Gaussian and theta is non-Gaussian. So theta, you know, is the parameter. But I mean, remember what I'm saying is that since x is the sum of two random variables, I can call W signal and theta is the noise, and you know what I'm saying is perfectly symmetrical. Now, so in order to compute the MMSC, I need to write a definition. Now, so I write a definition, easy. Okay, so let's start it. So theta MMSC is the mean of the posteriori. Perfect. Now what I do, I write the posteriori. When I write the posteriori, I remember that W is Gaussian and theta is not. Okay? So I generically represent, you know, my distribution theta and W. Now, you know what I mean. What I do, I need to write. I mean, this way. Looking here is integral, so that the mean is integral with respect to the dummy variable. Alpha is just a dummy variable of the a posteriori PDF. So it's P of theta given x, which is parameterized now with respect to alpha. So rewriting everything, I write it this way. Fine. Now you know, if I look at what is a Px, now the probability x is the probability here. But since these two guys are statistically independent, the probability of x is the probability of theta convolved with the probability of w. So I write this convolution into the denominator here. Okay. This second part is Pw of x convolved with P theta. what is written here. Okay? That's because of the independence. So now you know which is here. Now I move forward. Now what I'm doing now is skipping some analytics. When I skip some analytics, so which means to go from here to there, you know, there is some computation. Now, look at the booking case, but you know, what comes out is the following, that the MMC is equal to x plus this strange derivative with respect to x of the probability density function of x. Very strange. So it comes out that this one is that is the probability density function. So you know, let me write in a more, let me say, more extensive way. So this is the xk. So I take the xk and it's a probability density function of x computed in x equals xk. But now you know this is the function. So that is the behavior of the estimator. So that one depends on the probability density function of x. Now, since this probability density function of x is obtained here by compounding a Gaussian with a non-Gaussian, the overall is non-Gaussian. So let me say, if this px is Gaussian, then Gaussian means it's exponential of x minus x squared. So if I take the derivative of x minus x minus x squared, it comes out, when normalized with px, it comes out that the behavior is linear, as we proved before. But in the general case, as indicated here, is not necessarily linear. So we need to, we need to formalize, we need to customize in some special setting. So let's consider the case. Okay. So, you know, that's, but let's consider the case here. Let's consider this case. Assume now that my observation, xt, is equal to theta t plus w t. Now let's consider that this w is Gaussian, and this theta is not Gaussian, as in this case. But you know, as an extreme case of non-Gaussian, let's assume that it's plus minus 1. Telecom recognizes it's a binary communication. Oh, you know, let's consider the special case where, you know, theta is plus minus 1. So then, you know, x is non-Gaussian. Now we can compute the probability density function of x. Okay? And Telecom computed that, you know, they close the eye and compute. Okay? So then I can compute the probability density function of x. Okay? So the probability density function of x, in this case, is the composition of two Gaussians. So now you know, when I compute the probability density function, I can compute the, you know, my estimator, so my MMC estimator. Now, so my MMC estimator comes, looking at the formula, I need to compute the derivative of this behavior. It's very strange. And I need to take this derivative and divide by the behavior itself. So it comes out that the MMC estimate for that is equal to the hyperbolic tangent of the data divided by 2 times sigma w. So the behavior of the MMC estimate is approximately a sigmoid function which is smoothly going between minus 1 and plus 1. And if a sigma w, which is the power of the noise, is going to 0, this behavior is getting close to a sine function. Okay? So for sigma w going to 0, this smooth, non-linear estimator becomes a sine. Now, so if I need to say, what is the MMSC estimate of the value of the received signal if the transmitted, or if the theta is equal to 1, then you know my estimated value is not plus 1. It's a value that is different from plus 1. And it is, you know, is close to 0. Is pulled to 0. Is pulled to 0 by the fact that you know, the a priori information has 0 mean. Now, on the other hand, if I choose differently, if I choose the maximum a posteriori estimate, then the maximum posteriori estimate establishes that the estimate is plus 1 or minus 1 if depending on the value of x, which coincide with the sine function in case, you know, the probability of the two events are equal. This is the most conventional way to make a decision, because, you know, I have a binary variable which is a plus 1 and minus 1, and then I need to decide what is the value. Now, the maximum posteriori is a sine, and the MMC is a smoothed sine, if you like, okay? Which is this, this is given by the hyperbolic tangent. Now the telecom, you know, they know that it's comes from the information theory, and is a softer decision. These, you know, these hyperbolic tangent decision behavior. Okay. So now it comes out in our case from the MMC estimation, and the MMC is the body-central solution. Is the case where, you know, is minimizing the mean square error. More. Let's assume that, you know, I take another example. The other example is I have a data x, and which is a sum of theta plus w. Now theta, you know, is the value that is random variable that is labeled as noise is theta. So this now is noise, and this noise is non-Gaussian, and this W is Gaussian. So the behavior that I'm representing, you know, the kind of problem that I'm representing, is represented by this set of measurement where every now and then it happens a big spike. Okay, so, you know, I have some random process, bum. Then you have a random process, bum. Then you have a big spike like this. Okay. And my goal is to remove these spikes. So how to remove the spike? You know, in order to remove the spike, I need to model the random variables representing the spike. So I say that, you know, my data is Gaussian plus a non-Gaussian. And the non-Gaussian are the spikes. And so this model, you know, was originally defined, was originally proposed by, in 73, by a guy which is was called Middleton. And Middleton proposed this statistical model to describe the lighting effect. The lighting is when there are thunderstorms. Okay? So because when there are thunderstorms, any electronic equipment is in some way perturbed. Now the electronic engineers, they put a lot of capacitors around to avoid these big spikes, because otherwise, you know, the telecommunication system or so on, they cannot really decode the information. But I mean, it's these big spikes exist, and we did. It was in '89, 88, 89, okay? We were making some measurement in north of Italy about the natural electromagnetic field, and making these measurements in the electromagnetic fields. I mean, we started to measure some spikes, and these big spikes were anomalous because we could not understand why there were those big spikes. We were measuring the electromagnetic field, and you know, the low frequency electromagnetic fields. You measure that because you put the dipoles on the ground. And the reason to do that is because we were using a magnetotelluric method. I don't know if anyone knows that. No, no problem. Okay. So magnetotelluric is this. I'm preparing you for the break. So magnetotelluric is this. Okay. So you know, if you look at the ground, the subsurface of the ground, okay, is represented by a set of layers. So these layers, you know, they are characterized by different electrical impedance. Okay? So you have an impedance here, impedance E2, impedance E3, impedance E4. And you know, this is due to the layer structure. You are sitting here. Okay? You are on the top, like where we are. Okay? So, you know, if you measure the electrical field and the magnetic field on the surface, you get information about the electrical property of the subsurface. Okay? It's important to explore, to find if there is a mineral, if there is, I don't know, iron, and so on. Okay? So you get these layer structure. Huh? Now, but you know, what you measure here, really? You measure the micro variation of the magnetic field due to the rotation of the Earth, because the rotation of the Earth, you know, is in some way generating, is not uniform, and is generating a micro variation of the magnetic field. You know by induction that the electrical induction says that if you have a variation of the magnetic field, you get an electrical field. Okay? So that means that because of the rotation of the Earth that is rotating, you know, there is a fluid, you know, that's how the Earth is done, you know, so there is a fluid inside, there is a iron based, this fluid, and because of this variation of the speed of between outside and inside of the Earth, there is this, you know, this magnetic field outside. But you know, this magnetic field on the surface generates sometimes a small variation of the magnetic field. This a small variation of the magnetic field induces an electrical field that propagates underneath. So if you measure the magnetic field Hx, Hy, okay? X-ray, you measure three-dimensional, so Hz. And you measure, so you correlate this with the electrical field Ax, Ay, Az. Okay? So if you like, you know, it's H and electrical field E. Okay? So the relationship between them is the impedance. But now this impedance, it depends on the layer structure. So the low frequency component of this impedance measure the integral of these layer structure of the differential impedance for every layer, and the high frequency is measuring the details on the shallow part. So if you put this information together, you get a kind of imaging, so you get an electrical imaging of the impedance under the surface. So that was our goal. Okay? Now, you know, it happens the following, that this kind of measurement, when you measure the electrical field, you are very sensitive to the noise. So when you measure, you need to consider that the electrical field that we are measuring is very, very tiny. It's very small. Okay. So the problem is not that different from the gravity waves. Okay. So I mean, have you seen that it was discovered the gravitational waves? Huh? So it's very similar. There is a lot of noise around, and then you are measuring a tiny signal. Now, by the way, you know, at that time, it was a kind of pioneer work. Now it's a routine work. But you know, at that time we were enthusiastic and we worked on it. Now, so we started measuring that. You know, at a certain point, I mean, by the way, sorry, you open and close the bracket. You know, this kind of measurement is very sensitive to lighting. So it's sensitive to the lighting if the lighting happens within the radius of 300-400 kilometers. Okay, 300-400. So you know, and we made a measurement in a very clear sky. We knew that there were no thunderstorms. And, you know, and we started measuring the signal. And now the signal, you know, we measured. Okay, so that's a problem. The signal we measured, you know, was not small, but you know, was making this jump like that, this jump. You know, and we could not understand why we had this step line. Okay? So then, you know, we were desperate, really. We could not understand. Okay? So you search in the literature, nobody has ever seen that. So what is that? I mean, so now, you know, we started studying, we started to understand that is, for instance, this is the electrical field, like EX. And then we measure E1, just to say, okay? But you know, we noticed that this EY had a step that it was smaller. But this step was varying in time. So the size of this, if you correlate this with that, you know, is varying in time, okay? So now we start thinking, why is that? Okay, okay, you know, so this means night of nightmare, okay? Because when you are making research, it's like a nightmare. You think that all the time. Okay? Done. Okay? So you are like an hunter, you know. And there is, I don't know if there is a story, there is a scientific story that says that, that is the hunting attitude is the difference between men and women. Okay? So anyway. So then, you know, you are like a hunter. You try to understand why is that. Now we understood about that, but you know, it was really by chance. So we were on Sondrio area. I don't know, some of you might know that, but you know, there is a Sondrio, there is a city, and there is a valley. What is the valley? The name of the valley? Valtellina, right? There is a Valtellina. And now, at the bottom of Valtellina, this valley, okay, there is a train, okay? And the train is going, you know, along the valley. Not very often, but you know, it goes. We were here close to Monte Motarone. You know where is, you guys, you are from there, I don't know. Monte Motarone, is it somewhere here? Okay, there's a mountain, you know, a mountain here. So we were here, close to the mountain. So we were making measurement here because there was a strong interest to understand it. There was iron and so, okay? And so, you know, what happened? It happens the following. When there is a train is, that's how the train is done. That's what we understood, actually, okay? So after days, we studied, okay, how is the electrical power in a train. So the train is done in this way. So you give a power, and so, I mean, you put these second into the ground. So, and you have a pantograph, okay, so you give an aerial part, and you give the power on the other side. So when the train moves, okay, the train touches, okay, on the top, and get the current from there. So the current is going this direction, and then to the ground. So the loop is closed onto the ground. and then gets the power, okay, from the other side to ground. Now these two loops, okay, which apparently are small, they spread all over until our measuring point. And we saw what? We saw these, actually we saw this electrical field that because the train was moving, okay, we saw this electrical vector that was moving in time. And that was due to the fact that the train guy that was the driver of the train, I don't know the name, okay, the driver of the train was giving power and release. So for some reason we understood then that on the Valtellina you need to give power, release, give power, release, give power, release, and then that's what we measure. Okay? So I'm shrinking in a few minutes, okay, 6 months of nightmares. Huh? Then we understood what was that. Now, once you understand, you know how to handle. Because what we did, we made an estimator of the train. So we knew from far away if there was a train in Valtellina. Okay? Then, of course, we decided to make the same measurement during the night time. But since these steps were very clean, so essentially, you can take this value, pull it there, and the signal comes in. Because we experimentally found that if you remove the step, everything makes sense. But you cannot stay accepting that the steps comes from the even, okay? Perhaps, if your region, is this way, But you need to find a justification for everything. And then we found it, That's how we spend a lot of time studying and modeling the middle tone noise. And I show you how to treat the middle tone noise after the break.